Welcome to Homework Lib.
The goal of this question is to take a p-n junction with a given saturation current at a given temperature and figure out the voltage needed to produce a positive current of 40 milliamps. So we know we're looking for some I equals 40 milliamps, and we are given a saturation current of 6.4 milliamps, and we also have a temperature of 300 Kelvin. So if we look to our equation, we're given this is a constant, so is this, and we also have the temperature. So we're looking for the voltage V, as mentioned in the problem, but it's stuck up here in this exponent. So we're going to need to use some tricks using natural logs in order to get this down where we can deal with it a little better. So the first thing we'll do is take the natural log of both sides. So we get ln of I. Then ln of all of that. However, there's a little trick that whenever you take the natural log of two things that are multiplied by each other, you can separate that as the addition of those two things. And then we can leave this in its full form for right now. So just to show you an example, ln of A times B is equal to ln of A plus ln of B. So this is a very handy trick because we're also going to use it in taking apart our, in shuffling everything around here. So, and 1 is a little special because ln of 1 by itself is just 0. But eventually, if we shuffle these things around over here, so I minus ln is, and I'm still going to leave this over here because I want to be very methodical. Whenever you have a subtraction like this, you can write it, subtraction of natural logs, I mean, you can write it as the operand of the natural log being divided. So this is equivalent to this. Now we can finally rip this thing away. So the fact that the natural log of 1 is a bit of a special tool, you can go to any table, I guess, and find the various relations for natural logs and operations you can perform with them. And that'll be of great use because it's something that comes quite in handy. But we're going to split these so we get natural log of E, B, KT. I'm going to go ahead and move this bit over into here. And then, if you remember, the natural log of an exponent is just whatever is up here. So we finally get that, I'll just write it over here. The operand of the exponential is down on the ground. Okay, now we want the voltage, so then shuffling things around, we end up with our equation for the voltage of KT over E times the natural log of I over IS plus 1. And just as a check, we have this, and these are constants. So we can perform the plugging to see that the voltage is a paltry 5.12 times 10 to the minus 2 volts. So quite small, but that's the answer for part A. And then part B, which I'll go to a new page, but first I'll show what we're going to do. Part B, we're just concerned with this equation, where instead of, we're going to plug in for this V, the opposite of this one. So, going to the next page, we have I is equal to IS times E to the EV over KT minus 1. We're looking for I, but we have IS, so that's a known, E, and then we're going to say minus EV naught, because that's the one that we found. So just plug in that 5.12 times 10 to the minus 2 at the same temperature as before, and you get the negative current as negative 5.52 milliamps. So quite a bit smaller than the forward current.